Okay, in this video, we're going to take a look at something called equilibrium law. So equilibrium law is going to allow us to calculate the concentrations of both the reactants. So for instance, if we had something like A2 plus B2 forms 2AB, that equation, if we start out with an initial amount of A and an initial amount of B, we're going to make a certain amount of AB at equilibrium. And we just finished in the last video talking about that the system would undergo a change. There would be a shift. So let's just say we had 1 mole per liter of this, mole per liter, and 1 mole per liter of this, and 0 moles per liter of the product, because normally we start out with just the reactants in our flask. Then everything would shift in this direction. This would undergo some kind of negative change. Let's just call it negative X for now. This would also undergo a negative change. And this would undergo a positive change, which would actually be twice as big as the change of the decreases on the other side because of this 2 here. So we could say 2X. Right? And then we could calculate, since we know a little bit about equilibrium, we could calculate equilibrium values by adding down and getting things like this would be 1 minus X, 1 minus X, and this would just be 2X. Okay? So we can actually solve all of this and make it work. Now, the problem is we don't have any way of getting X. And so to be able to figure out what X is, how much of a change there was, we look at another value called the equilibrium constant. And that value is given by the letter K. And it's a value that at a specific temperature, so you must be at a certain temperature. You can't change the temperature. It has to remain constant. For a given reaction in a closed system, K will be a constant value. It'll always be the same, no matter what concentrations of products and reactants you start with, you'll always get this K value coming out to be a constant. And basically, we'll look at it in a little more detail in a minute, but basically it's a function of the concentration of the products divided by the concentration of the reactants. Okay? And so that ratio of products over reactants is a constant. And if that ratio is a constant, then that allows us to get back into this math down here and start solving these for these x's. Okay? So that's how we're going to go about trying to figure out concentrations. We need to know this K though first. And so it's either it will be given to you or you will be asked to calculate it, but you must have, if you're not given the equilibrium values for a particular reaction, then there isn't really any way of calculating out K. K is found experimentally. So in these first few questions, I'm going to give you all of the data that you need in this ICE table to be able to get equilibrium values and calculate K. And then in the next step, probably next week, we will take equations where you don't know the equilibrium values, you don't know what X is, but I will give you a K and show you how to solve for X. Okay, so that's kind of our ultimate goal. But let's start out by looking at how we find K for a reaction. Okay? Now let me just go over a couple of other things about reactions so that you have an understanding of what K means. In this reaction, chlorine gas, so that's this one here, chlorine gas, and CO2 gas, or sorry, just CO gas, carbon monoxide, and something called phosgene, which is a toxic gas that was used in the world wars, phosgene, sorry, and it is COCl2. Right? So the experimenter put a little bit of each one of these things into the flask. You can see that each one of these is not starting at 0. So we have all of those things inside the flask. And we see that after a minute or two, the concentrations begin to change as the system tries to reach equilibrium. And so we can see that the Cl2 is actually increasing. The CO is actually increasing. And the COCl2 is decreasing. So that means that this equilibrium system is actually reestablishing equilibrium by shifting toward the reactants. Okay? So we haven't seen that. I think in the previous questions I always had it shifting away from reactants, but because of the balance that's here, In order to bring this in so that all of these three concentrations start to become static, we see a shift in the concentrations by going to the left of the equation and making more of the reactants and using up some of the products. Okay. Now, what we can calculate is the ratio of these products to reactants. So we can take the concentration of this product and do a ratio with the concentration of these two reactants. And what we'll find out is we'll get a number, we'll get the number K. We'll get that constant, okay? Now, if we were to stress this system out again, and maybe for some reason the experimenter added some, well, let me clean off what I just wrote. You can see in this experiment, the experimenter somehow took out and removed some of the CO. We see this rapid drop in CO concentrations. So the experimenter removed some CO gas from the flask. And now we can see the response of the system. We can see that after that CO was removed, more CO was made to replace it. So we see that concentration going up. We also see the concentration of Cl2 going up. So again, this system is shifting in the left to the left or in the reverse direction. And we see the concentration of CoCl2 come down. And so that makes sense that again, there is a shift. But again, we come to a point where there's equilibrium and each of these things level out and seem not to change anymore. So now we're at a second equilibrium position. We'll call that EQ2. We'll call this one EQ1. What happens as long as nothing has changed in terms of the temperatures of the system, then the K value, this constant for the first equilibrium, is equal to the K for the second equilibrium. And that will remain true as long as we don't change the temperature of the system and what temperature the reaction is happening at. Okay, so this K value is a ratio of these concentrations of reactants and products. And we're going to use that ratio, that constant, to be able to fill in things that are changing. So even though these concentrations of EQ1 and EQ2 are different, we're able to use the fact that they are still in this constant ratio of K, or KEQ, as it's often called, K for equilibrium. We can then fill in some of the missing blanks that we might have in terms of what those concentrations are. Now, in this graph, just to finish this up, if you use these values, which we'll do in a minute, so you could use these concentrations that were here, and you calculated out K, and then we could call that K1. If you use these concentrations, these three, and calculate out K2, okay? Again, it doesn't matter that these concentrations have changed. Their ratio, the product between the ratio of the products over the reactants remains a constant value, okay? And that's what we're going to use as we move forward with the math. Let's look at this example again, just using some variables, and then we'll apply it to some real equations in a moment. But if we had the little a represents the coefficient, and then the big A represents the reactant, a little b coefficient, big B reactant, and then so on. So this would be A plus B forms C plus D. And if we were to write out what's called the equilibrium law, what it is we say that K, that's our equilibrium constant. So I'm going to say I call it the KEQ, and we're going to set it equal to the concentration of C raised to its power of its coefficient. It's just the coefficient from the reactant. There's nothing to figure out here. It's not like rate law where we had to figure out these little powers. It comes directly from the reaction. And D raised to the power of D. Capital A, concentration raised to the coefficient little a, over capital B raised to the power of B. So we have products on the top, products over reactants. And when you do that, you get a constant value called the equilibrium constant, okay? So this gives you a value that we can use if we want to do some calculations, or even to see if something is actually at equilibrium, because at equilibrium, if you were to measure the concentrations of all of these things, then it should come out to be equal to KEQ. And if it's not, Then for systems that are not at equilibrium, the ratio can be used to figure out which way is the system moving. Is it moving faster in the reverse direction or faster in the forward direction, right? So when we're not at equilibrium, what we calculate is, so we give given some data, we calculate Q, which is the ratio of the products over the reactants, but not at equilibrium. This is at some other time during the equilibrium process. So it could be back, let's go look at the graph here. It could be back in here where things are changing, and we know we're not at equilibrium. That we could still calculate out this ratio of products over reactants. Now, if we calculate out that ratio and we find out that that ratio is equal to K, then we know that our system is at equilibrium. So this is another way of mathematically finding out if something is at equilibrium. We can look at it, see if it's macroscopically stable, or if we have the data, we can calculate what's called the reaction quotient, Q, which is calculated using the same formula that we just talked about up here, but we know that it's not at equilibrium yet. But if Q equals K, that proves that we are at equilibrium. If Q is less than K, so that means that the value we get is smaller than the K value. The only way to make that Q value get bigger would be to make more products. Okay, I hope I'm not stretching the math here too fast. But if I wanted to make, eventually my goal here at equilibrium is to have Q equal to K. If I do my calculation at some point during my reaction and find that Q is less than K, then the only way to increase the size of Q would be to make more products. And in that case, our reaction is going to be shifting toward the right. And we're going to see more and more products being made. So we're going to see a shift in the forward direction, shift forward, and we're going to see more products made. Eventually, that will cause the reaction rates to equal out, and eventually that'll bring us to this point where Q equals K. Okay? But again, if we pick another point of the reaction and we calculate out Q and we find out that Q is greater than K, then we know we're not at equilibrium. And the only way to make Q smaller would be to use up some products and to make more reactants. And so if we have Q greater than K, then we need to take it and we're going to be shifting in the opposite direction. We want to bring it down, so we're going to shift in the reverse direction. Shifting in the reverse direction lowers the Q value, again, until these values get to the point where they equal K. Okay? So this is a way of mathematically looking at what's going on. If you could sample your system and figure out the concentrations of all the things that were in your system at any given point, you could calculate out this Q value, compare it to the actual K value for the equation, and know whether or not your system was at equilibrium, shifting in the forward direction, or shifting in the reverse direction. And we'll come back as we start to do some more questions and take a look at how we use that idea of a reaction quotient. Okay, so let's take a look at an example here with a real equation. This would be an equation where we might see the decomposition of water. So if we have water sitting in a sealed system, so we have, just do a sealed system, a box. If we have water sitting in the bottom of that box, some of it will decompose. Some of that water will decompose and it will turn into hydrogen and oxygen. Now that occurs at a very low amount. That occurs at a very small amount. So most of this H2 and O2, as soon as it's formed, turns back into H2O. And so this equilibrium is very much balanced on the side of the reactants. Very little water actually spontaneously turns into H2 and O2 gas. Okay, but it does happen. So if we were to write out an equation for this, what we would write as an equilibrium equation or an equilibrium expression, we'd say that KEQ is equal to, well, it's the products. So the products, the way it's written right now, is H2 raised to the power of 2 times O2 raised to the power of 1, because that's the coefficient in front of the O2, divided by H2O raised to the power of 2. And that's how we would translate this equation here, where we were looking at the rate law expression in general terms. That's how we translate it using an actual equation. So it becomes KEQ equals concentration of H2 squared times the concentration of O2 divided by the concentration of H2O squared. And that calculation will always come out to be a constant value for a given temperature. Okay. Now, there's a bit of a problem with this one is that you can't really have the concentration of a liquid. There isn't no way to measure the concentration of water. It's a liquid. It doesn't have a concentration. It's not a solution. It's a liquid. So because of that, when we write out these equilibrium expressions, this one actually will get simplified. And whenever you have something that's in a liquid form or actually in a solid form, both liquids and solids are not included in this part of the equation. Because liquids and solids are basically constant concentration, they don't change in concentration. They're actually embedded within this K value. So when we rewrite this, we would actually take this and rewrite it so that it looks like this. And so the K for this particular equation would be much simpler. We can actually lose the water. It has no effect on the calculation. And the ratio would just be the ratio of H2 squared to O2. And that would be the end of it, because you can't have the concentration of a liquid or a solid. We don't have one in this particular equation. Okay, and so that would tell us then for this particular equation, that's what the equilibrium law expression would look like. Okay, let's see if we can actually do something with one of these and calculate out a K. So this is on the lecture 2 sheet that I posted on the classroom. You have this data. You see we've got an equation here where we take H2 plus I2 forms 2HI. And we did the experiment. We've got data on 3 different experiments. We have the initial concentrations. So again, we could have like an ice table figured out for this. Not that I don't think we need one for this particular one, but we were given this kind of data. We've got the initial concentrations right here. And then on the other side, we have the equilibrium concentrations. We could figure out the changes if we needed to. But the question just asked us to calculate the value of KEQ. So all we really need are equilibrium concentrations, and we're already given those in this particular question. So there's really not much to figure out. And it does say that they're in moles per liter, so they do have to be in concentrations, and that's what we've got. It also tells us that it's a closed system, so we know that equilibrium can be established, and it specifies the temperature at which we're doing this calculation. Okay, so to solve this, all we need to do then is we don't need an ice table. We've got everything kind of right in front of us that we need. So we can just write out what we've got. And so first step is to write the KEQ expression. So we say KEQ is equal to, now these are all gases, so they all belong in this expression. There's nothing removed this time. So it's the concentration of HI squared, because that's the coefficient in front of the HI, divided by the concentration of H2, it's just to the power of 1, and the concentration of I2, which is also to the power of 1. So that's our equilibrium law expression for this particular reaction. It's products over reactants. And we know that when we calculate it, we're going to get a KEQ value that is a constant for this particular reaction. Now, because it's a constant, we can use any one of these 3 experiments. I'm just going to use the first one, but you should be able to go back and redo this calculation for any of these experiments using the equilibrium concentrations and get the same number every time, if the system was actually at equilibrium, which I believe it is in this question. Okay, so let's just use the first one. We started out with 2 moles of each of the reactants. We had none of it at the beginning. And then at the end, here's our concentrations for things at equilibrium. So let's plug those into our formula. So HI says 3.116 moles per liter squared over the H2 is 0.442 moles per liter. And the I2 is also 0.442 moles per liter. Notice I'm not putting in any, it is important that the concentrations, that these numbers are in concentration units of moles per liter, but don't worry about putting in the units, and we don't care what unit is on K. The units change for every equation. There isn't a standard unit for K, it depends on the equation. So, and it's not that important to us that we have that particular bit of information, so I tend to drop them. And that's a kind of generally established protocol. And then we just have to calculate out a number here. So let's get the calculators out and calculate that out. And the number comes out to be 49.7. 49.7. And so that's our KEQ value for this particular expression. When the ratio of the products to the reactants is equal to 49.7, we know that our system is at equilibrium. And it also gives us a little bit more information. You'll notice a big KEQ value, 49.7 could be considered very large. You'll see that most of our chemicals are existing as products. There's less chemicals as reactants and more chemicals as products. And if you look at every one of the experiments, when KEQ is greater than 1, we see much more products being made as a result of the reaction. Right? When KEQ is less than 1, then we say that the reaction favors the reactants. We don't make very much product. And when KEQ equals 1, we have roughly equal amounts of products and reactants. And so the value of this number is it tells us where the equilibrium point is for a reaction. And then as a chemist, you can look at that reaction and find ways of pushing this equilibrium, which is our next topic. How do we move equilibriums around? Because we don't really want equilibriums with Ks that are less than 1. That means most of our reactants aren't getting turned into products. We want Ks that are greater than 1 in most cases, so that we make as much product as possible. Especially if we're manufacturing something, we don't want lots of our chemicals left as reactants when we're done. Okay, so you could take a look at this. You could do any one of those trials, and you should, again, get 49.7 as an answer. You may want to do that just to prove that the Ks are actually a constant. Okay, the other question I have in that section, it looks at this equation. So it's taking nitrogen gas plus hydrogen gas to make ammonia, NH3. This is the Haber process we've talked about, I think, in a previous video. And again, calculate the value of the equilibrium constant for this reaction. If the concentration is measured at equilibrium at 500 degrees Celsius, we're found to be. So you're going to do the same thing. You're going to write an equilibrium law expression. You're going to plug in the numbers, and then you're going to solve it and get the K value. And that's all we're trying to do at this stage. So pause the video if you haven't already tried this one. See if you can write it out, and then I'll come back and we'll take it up. Okay, so the solution for this looks like this. First thing I would do is I would write down my K expression. So KEQ equals, now it's products, so NH3 squared over N2 with a coefficient of 1, so it's just N2, and H2 cubed. So there's a 3 as a coefficient, so we put a 3 there. And they're all included because they're all gases, and so they all count in this expression if they're not solids or liquids. And the next step then is to take the equilibrium values and plug them in. So NH3, it was 2 times 10 to the minus 4, 2.00 times 10 to the minus 4 squared over the N2 was 1.5 times 10 to the minus 5 power of 1. And the H2 was 3.45 times 10 to the minus 1, and then don't drop the exponent, cubed. Okay, And we'll run that through a calculator. And we get 0.0, let's just go 0.065 as an answer for K. Okay, so that's a K that's less than 1. And that makes sense because this equation originally, the Haber process was looked at in terms of making ammonia. It actually tended to be toward the reactant side. It did not make a lot of ammonia, and the chemists had to work very hard to set this equilibrium up under certain conditions so that we could shift that equilibrium toward the right, and then it would make more products. So in the way that the Haber process is actually set up to work in the real world, the conditions under which it occurs are not just at 500 degrees C. They change the pressure and do a few other things to make the reactions more favorable, and they can actually push that equilibrium so that it goes toward the NH3 side of things. Because if you were to make ammonia trying to use this process, according to this number for K, most of your product would actually be not made. It would mostly be existing as reactants. And so there's one last one. Again, I'll pause the video here for a minute, and then I can show you the answer for this last one, and we'll see how we're doing with calculating equilibrium constants. Okay, and so the answer for this final one looks like this. We would write out the KQ, which would be equal to the concentration of methanol over the concentrations of CO and H2 squared. So again, remember to bring down this coefficient. Put the 2 there. This has a coefficient of 1 and another coefficient of 1. And then we plug in some numbers, and we get the 0.21 for the concentration of the methanol. We've got 0.079 for the concentration of the carbon monoxide, and 0.158 squared for the term that involves the hydrogen. And then when you crank that through your calculator, you end up with 10.6, or I suppose if we rounded that off, it would be properly be write it as 11. So that's the KEQ for this particular reaction at 327 degrees Celsius, no matter what, as long as you put in some of each of these things and it's allowed to reach equilibrium, those concentrations will always come out to be this number, 10.6. Okay? So that's what we'll use in the next set of videos. We're going to take a little break from the math and look at something called Le Chatelier's principle on Friday. And then once we have that under our belts, we'll come back and look at the math here, understanding how chemical equilibriums can shift, and then applying this this equilibrium law expression to some more questions where we don't know the equilibrium concentrations and we're asked to find them. Okay, so post your questions if you have them, and that's it for now.